All right, here we go. Let's have a look. So close up your profile, phones away, etc. All right, so here's an example I want to look at. Newton's third law stuff. We started talking about this yesterday. Okay, so let's look at this one. We've got physics professor. Physics professor pushes a cart of demonstration equipment to a lecture hall as seen in the figure below. Her mass is 65 kilograms, the cart is 12 kilograms, and the equipment is 7 kilograms. Calculate the acceleration produced when the professor exerts a backward force of 150 newtons on the floor. All forces opposing the motion, such as friction on the cart's wheels and air resistance and all that stuff, all resistive forces combined, we'll just call them friction, and they combine to amount to 24 newtons. Okay? So what are we going to do? That's a lot of information. Yeah. A lot of information. So think about it. Here, let me roll this down just a little bit, or so you can make this a little smaller, maybe. Okay, there, that's everything. Okay, so what are you going to do here? We're trying to figure out what the acceleration is produced on what? And? Person and? Equipment on the car. Everything, right? They're all moving together, okay? So let's draw a free body diagram. What's that going to look like? Let me see. What are the forces that we need here? Let's identify first, what are the action-reaction pairs? Okay, foot in the floor. Right, foot pushes back on the floor, floor pushes forward on the foot. I mean, the professor.
Professor in the cart.
You could just say, that's professor instead of foot, I guess, right? Okay, what else?
Professor in the cart.
Okay, professor pushes on the cart. So if professor acts on cart, then the reaction force is cart acts on professor, right? So there's an action-reaction pair. What else? Cart in the ground. Yeah, there's going to be a vertical force there, right? Okay. There is one other one that's not totally shown here.
Friction and kinetic force.
Okay, so the friction, what's the frictional force? Now we got to be careful with this because friction is the label of the force, right? Like we would say weight is a label of gravitational force. But if I'm talking about the weight of this pen, that's part of an action-reaction pair acting between what two objects? Not my hand. Pen in the earth, right? Earth pulls on pen, pen pulls on earth, right? Okay, so the friction is just similarly, it's just the label of a force. The frictional force is the force that's acting between which two objects though? Let's just assume there's no wind resistance. Let's just say that it's all frictional force with the ground.
The earth and the entire system.
Okay, well the earth and the cart in this case, right? Cart's what's experiencing the friction. Does that make sense? If there were no friction acting, that vector would be gone, right? Sometimes it's good to use the principle of exaggeration, and a lot of times what I like to do with situations like this is imagine there's a loose carpet on the ground. If there's a loose carpet on the ground and there's no friction, the cart's going to roll along that pretty easily, right? No problems. But if there's a loose carpet and there's a lot of friction, there's a lot of friction between the ground and the cart, maybe the wheels need oiling or something, then what's going to tend to happen to that loose carpet as I push it? Okay, yeah, it's going to get balled up in front of the right? It's gonna push the, does that make sense? Okay? And so you can see then that the frictional force is acting between the ground and the cart, right? So if we call the action force, the ground pushes on the cart frictionally, right? Then what's the reaction force?
Cart pushes on the ground.
Cart pushes on the ground. Okay. All right. So if we're trying to find the acceleration of the whole thing, which forces of those would probably be important? Which action-reaction pairs?
The one on between the cart and the ground.
Cart and the ground. Okay. What else?
Cart and professor?
Cart and professor, what do you think? External or internal force? Internal, right? So that's one we don't really need to worry about. If we're talking about everything together, this is all considered to be part of one system, right? And that's internal to the system. And so that one, as far as we're concerned, maybe the professor's hands are glued to the cart. We don't know, right? I mean, it's irrelevant, right? But they're one and the same for the purpose of this discussion, right? Does that make sense? I mean, it might as well just be a motorized cart. Okay, but I mean, she's the motor. Okay, so what are the action-reaction pairs that we probably need to consider then? Just not that one, right? Just that one and that one. And how come? Those are the action-reaction pairs where there's an interaction of the system with something outside, meaning the earth or the ground. You get that? Okay. I mean, if we wanted to get very specific, we could look at like a free body diagram for this would be what this is the okay. Here's our system, isn't it? Right there. That's everything. Right. We've got the frictional force pushing backwards. We've got the pushing force, right? The floor pushing on the system, on the professor who's part of the system, pushing forward. And then we've got these vertical forces that just balance out, that don't do anything. Normal force and weight, right? We don't really need to worry about those if we're calculating acceleration, because the acceleration is all horizontal. Okay? Question?
So I know the backwards foot force between the foot and the floor is discarded because you're moving forward, but how is it just?
Okay, because look there's an action-reaction pair. In order for me to walk forward, what do I have to do? I got to push on the ground, and if I've got ice coated with WD-40, I can't do that, right? Then I'm just going to slip in place. I'm just going to kind of scissor in place. I'm not going to go anywhere, right? So I got to be able to push off on the floor, and whatever force I'm applying to the floor, that's also the force that's being applied to me to push me forward, right? So that's what we might call the driving force or the motor force, right?
But if the forward force of the floor pushing you forward is represented, why isn't the foot on the floor?
Okay, because what are we trying to find? We got to be specific here, but it's pretty strongly implied that we're trying to find the acceleration of the professor and the cart and all the supplies, and not the acceleration of the earth, right? Does that make sense? So this is the force that's going to tend to roll the earth backwards a little bit, right? This is the force that's accelerating the system of the cart, the professor, et cetera, forward along the ground. Okay. So what are the forces that are acting horizontally on the system? Well, what are they? That one, right? And that one. Does that make sense?
Yeah.
Okay. All right. So then this free body diagram makes sense? I mean, that's kind of weird to say force on the floor. We probably would have called that previously, we would have called that like pushing force or something, right? And do we need to be specific and say it's the force on the foot or the force on the floor? No, those are just the different, those are the action-reaction pairs associated with what we might call the pushing force, right? Or the, I don't know, how would you say it? I mean, I guess how would you describe that? I mean, I would call it the motor force or the driving force, right? we're pushing on the ground, and that's providing the force that drives the whole system forward. In the context of like a car, like we've talked about before, we would have called that the driving force because it's what the wheels are providing to the car that's pushing forward against friction. You get what I'm saying? It doesn't matter what you label it. Whatever you want to call this, this is the force that's driving the whole system forward. This is the horizontal force that's tending to push it backwards a little bit, right? Okay, so then if we want to calculate the acceleration, what do? We got an equation of motion here, right? All we really need, and they give us the magnitude. What's the magnitude of that force? The frictional force?
24 newtons.
24 newtons. What's the magnitude of the driving force?
50.
150, right? That's how far she's pushing on how hard she's pushing on the floor. So therefore, the floor is pushing her forward with that much force, right? So that's 150, and that's negative 24, right? Okay, so the math is going to be not a big deal here, really, right? The math is just going to look like, if we want to look at the horizontal component of the net force, we had was it a positive 150?
Yeah.
Minus 24.0 newtons equals what?
126.
126. Right?
How'd you get that? Oh, you're just adding those up. Oh, I got you. Yeah, okay. But what's that equal to by Newton's second law?
Mass times acceleration.
Mass, okay, what's the mass going to be in this case?
All of them added up together.
Yeah, the mass of the system that we're looking at, right? See, this is system one. Of these two choices, we're looking at system one. So we gotta consider the mass of everything in system one, which is 7 plus 65 plus 12, right? So what is that?
84.
84, okay? So then that's just equal to 84 kilograms times A, right? That's pretty easy, no big deal. So all we gotta do then is the simple equation. What'd this work out to be again?
126.
126 newtons equals 84 kilograms. And I included I don't know why I included the units, but I did. So if I divide both sides through by 84 kilograms, well then, what is a newton going to be in terms of units? Base units. Newton is the unit of force.
Kilograms times meters per second.
Yeah, kilogram meter per second squared. How do you always remember that? Because F equals ma, so units of mass times units of acceleration, standard units would be kilograms times meters per second squared, right? So the kilograms would cancel, and I'd just end up with meters per second squared, like I should, right? And so what's that give us then if we do this? We're going to keep 3 sig figs, looks like. So what's A?
1.50.
Say it again, 1.50 meters per second squared. Make sense? Okay, all right, good. Okay, how about this guy? Calculate, let me do something. Calculate the force the professor exerts on the cart using any data from the previous example. Okay, so we remember all the masses and everything, right? How are we going to do that one? So this is just a little bit different, right?
You don't need.
And do you guys see what I'm getting at here? I mean, you have to carefully consider the system that you're talking about in order to set up the free body diagram, right? There's a lot of moving parts in this one. But if we're only interested in the force the professor exerts on the cart, how are we going to do that?
Well, you only use the mass of the cart and the equipment.
Okay.
Yes, sir.
So what's the system we're interested in then?
Just the cart and the materials.
Cart and materials. So that would be system 2, right? The professor is now outside of that system. We're only considering the cart itself, right? Okay, so what are the you know, just, we don't need to consider the vertical forces, we'll ignore those, they're gonna cancel. What are the horizontal forces acting on the cart?
Friction in the professor.
Friction in the professor, right? Does that make sense? Okay, so the free body diagram just looks like that, then, whoops, that's the wrong one, isn't it?
This is bottom.
Oh, there we go, there's the bottom one, there we go. Okay, so, yeah, system two, so the professor pushing forward, friction pushing backward, you know, we can forget about the vertical stuff. So the free body diagram this time looks like, what? What's the positive force?
We don't know.
We don't know, right, we'll just call it F sub P. What, I'm adding up all the minus
Friction.
frictional force, okay, equals
And
MA. And in this case, M is gonna be mass for system two, right? Okay, so then,
Acceleration.
so we know the acceleration, right? What do we need to, we know the acceleration, we know the mass, but we don't know the other stuff, do we?
You know the,
it gives us.
Oh, we know the
Yeah, we know
frictional,
the
we know the
frictional
frictional force,
we
right?
don't know the.
I forgot about that, but we don't know the pushing force.
Which is-
Okay. So we can plug in numbers. So F sub P, do you guys remember what was it? 24, wasn't it?
24.
F sub P minus 24.0 newtons equals M, and that was 12 and 7, so 19, right?
19.
19 kilograms times A. And A was 1.50, right?
Yeah.
Okay, so we can mark that too. Okay, so then all we gotta do is just add 24 newtons to that, right? To whatever this product is. So the pushing force is gonna be 24.0, we'll just not worry about the
28.5,
units,
I think it is.
plus 19.0, I think it was. Didn't, they were out to, weren't they? Weren't they out to the tenths? Here's a good chance for a little review. So if we're adding up masses, how many sig figs do we really get to keep for the masses there?
Two.
We actually get to keep 3. How come?
Because
Because it goes out to
It's
the
addition,
tens.
so you do the farthest.
Ah, good. It's addition and we're adding up, and that we almost never do that. But when we just add up a bunch of stuff, remember, we keep the most precise, or the least precise digit that we're adding, right? So when this one goes out to the tenths, that one goes out to the tenths, so the sum is 19.0, right? So it's actually 3, okay? That's kind of tricky. Okay, and that's gonna be kilogram meters per second squared or newtons, so we're getting newtons. What was the answer to that again?
28.5. Or,
It's 52.
no, that was
Oh.
19.
19 times 1.5 is 28.
Oh, gotcha, okay, so then, so what is it, what's the whole thing then?
52.5.
I heard 2 different answers.
52.5.
Yeah.
52.5 newtons, okay? Make sense? Okay, good. All right, how about something like, well, something like this? Just figure out what that is? It's kind of interesting. When a softball with a mass of 0.18 kilograms is dropped, its acceleration toward Earth is equal to g. The acceleration due to gravity. What is the force on the Earth due to the ball, and what is the Earth's acceleration?
When
Okay.
Lauren throws it at 207 miles per hour.
There you go. Exactly.
That's
The earth doesn't.
Well, let's first of all, let's figure out what is the weight of the softball.
0.18 kilograms.
0.18.
Oh, yeah.
Well, that's not a weight
That's a mass.
That's a mass, good.
Hmm.
A weight's a force, right? So,
The mass times that.
It's about 1.7.
so
1.8.
how do I find the weight then? If the mass is 0.18 kilograms, it's
Times
times g, yeah, times 9.8. So the weight is 1.6 to our number of sig figs, I guess it's only 1.8 newtons. Okay? So what do you think, what's gonna be the force on the earth due to the ball? Tiny?
Yeah.
What do you think?
Negligible.
What's that?
Negligible.
Negligible? Do we have a different answer?
I don't know. It's put it in my notes.
Something like that's a number times 10 to the negative 25 or something like that. So
No,
very small.
no.
Well, the force would be,
Force
force would still be considerable, it just wouldn't do anything to
In
it.
fact, it's how much? Did I hear you guys say?
4.7.
It's that.
Yeah.
Right?
Yeah.
You get it? It has to be, doesn't it? That's the weight. What's the weight? The weight is the force of the earth on the softball, so the reaction force is the weight of the softball and the force of the softball on the earth. It's the same thing, right? But what I think what you were getting at was that much force is it's gonna produce a negligible acceleration, right? So if we wanted to calculate the acceleration, that's easy to do. Might as well just, it'll be funny to look and see what it is. So we know that F equals ma, so A equals force divided by mass. So if we do this one, we're gonna get this number divided by, because that's standard units, divided by 6 times 10 to the 24 kilograms,
Oh my.
is gonna be a pretty small acceleration. So yeah, about 2.9 times 10 to the negative 25 meters per second squared. That's not very much. How long would it take for the Earth to move 1 micrometer, 1/1,000,000th of a meter, with that much acceleration? What do you think? Let's hear your guesses. How long is it going to take for the Earth to move 1 micrometer, 1/1,000,000th of a meter, with that much acceleration acting on it? If those are the only two objects in the universe, and we're providing that much constant force to an object the size of the Earth, what are your guesses? What do you think? I'm just kind of curious. It's just in the blue. Just out of the blue.
1 decade.
Here, everybody, we'll just make
A
this.
million years.
Everybody just write down. This is, I mean, you're not going to have any idea. But let's just kind of see. We'll just have a little lottery
How
here.
long will it take?
Oops. What do we? Just write down your guesses.
3 seconds.
And you got to write them down within
You said,
10 seconds.
you said micrometer?
Are you kidding
Don't
me?
even know what it's supposed to
I don't
be.
even have a pencil out.
Micrometer or,
Can you tell?
or
1
millimeter?
micrometer.
Hmm.
Okay, so what do we know? And by the way, this is a little bit hokey because they're center, well, it's really not hokey at all. I mean, the Earth is going to, we always want to know how much the Earth's going to get pulled by a softball. Technically, if we were doing something like this, if we're going to be really accurate, we'd have to take into account the fact that their centers are getting closer together, right? We don't have a tool for doing that yet. That's coming up soon. It's called the law of universal gravitation. But for now, we're just going to assume that the force is constant because it's a very short distance, right? What do we know kinematically here? What's the initial velocity of the Earth?
0.
0. It's at rest. The acceleration is
That tiny thing.
there, right? What's delta x?
1 micrometer.
So 10 to the minus 6 meters. And the time is what? Okay, so what's the kinematics equation that's going to do the job for us this time?
Delta x equals 1/2 acceleration times time squared.
Okay, so it's going to be the number 3, isn't it, right? So we got this guy, so whoops. Equals v naught t, which is 0, 1/2 at squared. Okay, so all we got to do then, if we solve for t, what's t going to be? We're going to square root something, but what's the fraction we're going to square root? We got a delta x on top,
2 delta x.
2 on the top, because we're going to multiply by 2, a on the bottom, like so. Okay, let's do this. So we end up with the square root of 2 times delta x, so that's 10 to the
Oh my
negative
gosh.
6,
Don't want to know.
divided by the acceleration, which is that number, that number.
It doesn't
Oh,
put it in
darn
the
it.
bottom, so you're gonna have to manually put it in.
Or just.
Oh, you can't do that? Seriously?
Or if you
Or
put, or
answer.
if you do answer,
Second,
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 the
second,
negative
second,
sign.
second
Oh, okay.
negative sign.
Oh, that's kind of a
It's
bummer.
because when you go up, it goes up into the top of the
Oh, I
fraction.
got you.
Here.
We'll just-
You put entry, not answer.
Oh, okay. I can't roll back here. I'm not gonna use that dumb fraction temper, that's too hard. So we get the quantity 2 times 10 to the negative 6 divided by, oops,
Push the arrow.
there we go, divided by that guy. Much better.
And this square root of
Okay, so it's that many what?
Isn't it that the square root
The
of
square root, you need the square root of that.
Oh, I got square root of 2, you're right. No, I did not, oh, I didn't on this one, did I? Square root of that. So that makes it much more manageable. Okay, now that is that many what's?
Seconds.
Seconds, standard units, right?
Divide by.
So it's that many seconds, so let's put this in terms of years, how about, right? So we're gonna put this in terms of years, there's 3,600 seconds per hour, right? So first, let's divide by 3,600. So that's how many hours, right? So we gotta divide by 24 to find out how many days.
Yeah.
Okay, divide by 365.25 to find out how many years. I'm kinda curious who got this.
Oh, you didn't
Oh,
like
wait,
divide
Oh,
by
whoops, you're right, I didn't.
clear.
I know. I just know it.
So,
Whoa.
oh, hang
Hold
on.
on, just hit.
Just go.
Yeah, I know, I see what I did, I just hit divide, yeah. Divided by, oh, no.
Uh-oh. Here.
I'm so screwed up. Let's go grab that number. That number divided by 365. 0.25. So it'd take, gosh, in the course of, I mean, you know, like, of just a long, healthy life, you could observe the Earth moving 1/1,000,000th of a meter in the presence of the force, gravitational force of a softball.
You have two
Nice.
softballs.
So what do we have? I'm kind of curious. Anybody,
I
that all close?
One
You
century.
had double that?
Yeah, because I grabbed by half,
You had how many years?
164.
Oh, so you actually did the calculation.
I had
Yes.
one,
Oh.
one century.
Who had
I got it wrong.
a reasonable, any
I had
guesses?
a century.
A century? Are you kidding
Yes,
me?
Santa did, but we came up with it together.
I guessed a decade and she asked me what to guess. I told her a century.
That's pretty good. Century's pretty
Or
close.
plagiarize.
I knew that
Pretty
you
close.
guys do.
Yeah, I was like, what is wrong? Everyone's supposed to. That's just the 40.
All right.
42 what?
That's it.
It's 42 something technically.
So
Hey, it's actually like, it's actually like, if it was
Okay, what about this one?
40 off.
Okay, you see the situation here, right? 65 kilogram boy, 45 kilogram girl using an elastic rope while engaged in a tug of war on an icy frictionless surface. If the acceleration of the girl toward the boy is 3 meters per second squared, find the magnitude of the acceleration of the boy towards the girl. Well, I mean, how would we do that one?
set the forces equal to each other.
So what would be, how many forces are acting?
Two.
There's one, isn't there? There's one force acting between two people, right? So the action force could be considered boy pulls on girl, and then reaction force would be girl pulls on boy, but that's just one force shared by two objects, right? Okay, so if the acceleration
This would be really boring.
of the girl towards the boy is 3 meters per second squared, how is that useful?
Because then the boy
Because
toward the girl is also through.
The forces have to be equal.
The forces have, but that's not a force, that's an acceleration.
You can use the acceleration and the mass to find the force.
Okay, good. So F equals ma, right? So the force on the girl F sub G, the force on the girl, is gonna be her mass, which is 45 times 3.0 meters per second squared, so what's that giving us? 135
Mhm.
newtons? So that's the strength of the force acting between the two, right? So if we wanna find the boy's acceleration then, we know that F
just
sub
135.
boy
Divided by.
equals mass of boy times acceleration of boy, so the acceleration of the boy equals the force acting on the boy, which is that, same force,
Divided by the mass.
divided by the mass of the boy, right? So 135 divided by 65 is about what?
2.08.
2.08. So about 2.1 meters per second squared, right? Make sense?
Yes.
Okay, how much time we got?
No.
9 minutes.
Not enough. Okay, so you guys can work on the Newton's third law experiment. So what I want to do, I'd like tomorrow is a great Friday thing. For tomorrow, I want to, so one of the big projects we're going to do is a trebuchet battle. Okay, the trebuchet battle will not happen for a while, but there will be teams on the trebuchet battle. So we could, let's go ahead and, so how many we got? 3, 6, 9, 12, 14 in here. So let's do, no, we'll just do 4 groups of 3/4, okay? Do you guys, is that right? 4 groups of, yeah, 2 groups of 3, 2 groups of 4, right? Okay, do you guys want to, now, I can do this one of 2 ways, and I haven't really decided. I'll take a little input from you, but I reserve the right to make this decision. So do you want to pick your own, how many people would like to pick your own groups? How many people would like me to randomly pick groups? Okay.
The girls, cause we get left out.
Oh.
Not
We'll
that
have a
we
nice-
don't with each other, but.
Silent I's decision is solely
Okay,
based on
so-
skill.
So,
And resources available.
I'll mull that over, but in the past, I've always tended to like make these groups myself. However,
We
I
should
will
do,
give you a little leeway because the work for this project is gonna be done outside of class. And so I do want you to, we gotta kind of think about how we're gonna manage this, because this is not something, well, all I'm gonna do on this, and the project is way, I mean, we'll do this in the spring, so you got a long time to think about this. But essentially, what I'm going to do is I'm gonna give you the restrictions for a trebuchet. And you don't even know what a trebuchet is yet, but you will after tomorrow.
Yeah,
Okay, well, maybe you know what a trebuchet is. Okay, so, but a trebuchet is not a catapult. Trebuchet is different than a catapult. The definition of a trebuchet is that it's a gravity-powered siege engine. That's where all the energy comes from gravity. Okay, so what I'm gonna tell you is just simply what you can use for projectiles and what the dimensions of the throwing arm need to be. I don't care what you use to build the base of the trebuchet. You could use, it could be made of gold for all I care. All I'm gonna tell you about, though, this is gonna be the big engineering restriction, is gonna be the throwing arm. The throwing arm is what limits the ability of the trebuchet. I mean, that's gonna limit you a little bit. I mean, you can't throw a ton with a chopstick, you know, I mean, it's gonna be something, and so I'm gonna modify what we did last year slightly, so it's a little less, so they're a little smaller than what we had last year, but it'll be something on the order of like a piece of dowel that is gonna be, you know, yay big around and about yay long, okay? The way this works then, the competition, competition's at the end of the year. I'm also gonna give you, in addition to that, you're gonna have the materials list that you can use to build your castle or castles. The way this works, at the end of the year, we will randomly pair off in a bracket and you'll go head to head in trebuchet wars. You start off a fixed distance apart and there's a little bit of luck involved. So you're gonna roll a die and the roll of the die determines your combination of incremental movements and or shots at the other person's castle. The goal is to knock down the army man standing inside their castle, okay? So you kind of get the idea, right?
What if you build each castle with the person?
Well, you can't though, because the materials are limited. So it's gonna be limited to, like typically we use a combination of graham crackers and you can use graham crackers for the walls. And you can use either icing or I will allow hot glue only at the joints of the walls. You can't, it has to only be for the purpose of sticking graham crackers together. I'll give you all the specifics soon, okay? But what I want you to be thinking about, how you're gonna engineer this. There's a lot of engineering involved. And I, rather than wait until we've talked about all this stuff, I think we're at a point now where you can start to think about it a little bit, and when we get into rotational mechanics, you'll be always in the back of your mind thinking about trebuchets, which is good.
I think we should stock up
On gingerbread houses?
Christmas time is hot.
Oh, that, you know, that would be, post-Christmas gingerbread houses would be dirt cheap.
And they'll be
That's
stale,
good
so they're
thinking.
harder.
They're not like graham crackers that
Christmas
has a
store.
preparation, like, you know.
Yeah,
I don't have any
okay, that's a possibility, that's a possibility.
Good thinking, Lily.
All right.
That's a very good idea.
So we could.
We'll coat everything in frosting.
Yes.
It is.
Yes.
So, can we start building it?